Okay, now let's go back to our discussion of making better semiconductors, right? We said that like for a pure silicon crystal, the only way to actually have more free electrons is to increase the temperature. And we realized that's not the way we want to go, right? Um, the idea behind having more electrons, or like the idea behind extrinsic semiconductor, is something called doping, right? So what does it mean? It means that it really comes from the idea that there's no reason for us to actually have a pure silicon crystal. There's nothing amazing about having a pure silicon crystal. They could actually basically inject or diffuse some sort of impurity into that crystal. And if we do that impurity, or if we actually inject that impurity into a crystal in a smart way, we can have extra electrons or extra holes inside our crystal, which are going to help us with better conductivity. Okay, so basically the idea of actually injecting some additional material into our pure silicon crystal is called doping. So we're basically doping our crystal to have a better performance. And then how do we do it, and what material we're going to use? Well, if the base of our crystal is a group 4 material like silicon or germanium, we could dope with type group 5 material such as phosphorus. This is the most popular one. Or we could do it with group 3 material such as boron, right? And we're going to see why these two types. And then we're going to call, if you inject group 5 material, we're going to call it N-type semiconductor. And if we do it with group 3, we're going to call it P-type, right? I know all of these might be confusing, but in the next couple of slides, you're going to see why we call it N-type, why group 5, why group 3, what's the point, and what is the reason behind this, right? But I just wanted you guys to actually look at this little piece of periodic table to know where does the phosphorus, to kind of like get reminded of where is the phosphorus and where is boron with respect to silicon and germanium. So let's see what happens. So if this is my intrinsic semiconductor, this is my silicon crystal without any kind of impurity, and we have these covalent bonds and these valence electrodes are shared between different silicon atoms. Now let's say that somehow chemically or with some other ways, we don't care about that, somehow a phosphorus atom is introduced into this crystal, right? So if we somehow put this phosphorus atom in there, one thing we can notice is that since phosphorus is of group 5, it's going to have 5 free electrons, or 5 electrons in its valence or outermost shell. 4 of these electrons are going to be shared with neighbor silicon atoms, and one of these is just going to be there, well, not shared or not bonded into any of these covalent bonds, right? So with this, by introducing a group 5 atom in there, into our crystal, we can see that we're going to have these free electrons per atom, per phosphorus atom, without even needing to actually break any of these bonds. Okay, so that's how actually we can create more free electrons without increasing temperature, without needing to actually break any bonds or anything. And that's why we call it doping. We're actually doping our semiconductor crystal with more and more. The more of these phosphorus atoms I actually introduce into my crystal, the more free electrons I'm going to have. So I can actually adjust the level of number of electrons, the level of the conductivity level of my crystal by adjusting the number of phosphorus atoms that I introduce into this crystal. Okay, so we call this extrinsic silicon because it's not intrinsic, because it's not only silicon, it is, well, silicon and a group 5 type of material, or N type of material. And because, well, it's adding a negative charge. So like we have two different charge carriers, right? So we have electrons and holes, electrons representing the negative charge carriers and holes are representing, well, the absence of electrons or the positive charge carriers. Since we're introducing an extra negative charge carrier into this crystal, we're going to call this negative type silicon or n-type silicon, right? Negative comes from the extra negative charge carrier. Okay, now how much is the typical value for these donor impurity, and why do we call it donor? So these phosphorus atoms, we call them donor because they donate an electron to us, right? To our crystal. So donor means it refers to the p atoms that donate an electron to our crystal. The impurity level is somewhere between 10 to the power of 15 to 10 to the power of 17 centimeter cubed, right? So that's the number that we know that if we're in that range, we're going to have a good semiconductor. Depending on how much conductivity do we want from our semiconductor, we increase or decrease the level of impurity, right? Still, you can see that if the number of atoms are 10 to the power of 22, even when we are actually at 10 to the power of 17, we're saying that for every 100,000 atoms, we're going to have one. For every 100,000 silicon atoms, we're going to have one phosphorus atom. So that's good enough to have a really good semiconductor, really good level of conductivity, right? Compare this 100,000 to 5,000 billion, right? So you can imagine that, like, yes, it's actually the ratio is actually pretty large. Every 100,000 is actually pretty large. It's a pretty large number, but compared to every 5,000 billion, it's, well, pretty much nothing, right? The other thing that it tells us is that this is the reason that we don't call this semiconductor phosphorus silicon semiconductor, because the ratio is actually quite high. So like the ratio of number of silicons over number of phosphorus is actually pretty high. It's every few hundreds of thousand silicon atoms, we have one phosphorus atom. So still we can say this is a silicon crystal, but we also need to say it's an extrinsic silicon crystal to kind of highlight that it's not a pure crystal. So the next question is, what's the density of electrons? Now that I've added these phosphorus atoms, how many electrons do I have here? Let's say that I have added 10 to the power of 15, or, well, let's say that the density for donor density or donor atom density of, let's show it with ND, of 10 to the power of 15 to 10 to the power of 17, I would say the number of electrons or the density of electrons, N, is pretty much equal to ND. So what I'm saying is that, what I'm claiming is that the number of free electrons is pretty much equal to the number of additional phosphorus atoms that I've added, or the number of donor atoms that I've introduced into this crystal. And you might think that, well, why don't you consider the free electrons that were there even before introducing the phosphorus atoms, right? I had some free electrons there because, well, I was operating in room temperature, and at room temperature, even with a pure crystal of silicon, I still have some free electrons, right? But if you think about it, we did calculate the number of those free electrons. It was in the order of 10 to the power of 10, right? So if I calculate the number of free electrons, and I want to do it exactly, N is actually equal to the Ni plus Nd. But if Ni is 10 to the power of 10 and Nd is 10 to the power of, well, somewhere between 15 to 17, you can see that the addition is going to be 10 to the power of, well, 15 to 17. It's not going to, that 10 to the power of 10 is, it has basically no impact on the addition, right? It's kind of like adding 1 plus 100,000. Well, it's still going to be 100,000. You can still approximate it with 100,000 without losing any accuracy, right? So n is going to be equal to nd as long as nd is much bigger than 10 to the power of 10, which is the number of number of free electrons in an intrinsic silicon crystal, right? So what about the number of holes? Well, we can use that equation that we found in the previous slide, that np is equal to ni squared. So therefore, the density of holes is going to be basically ni squared divided by n. Now, for an ni that is 10 to the power of 10, the ni squared becomes 10 to the power of 20, and n is 10 to the power of, let's say, even if it's the smaller one, then 10 to the power of 15, it means that p is going to be 10 to the power of 5, which means that it's actually pretty low, right? So before, in an intrinsic silicon crystal, I had the number of electrons and number of holes equal to each other. Both of them were around 10 to the power of 10, right? Because we said that, well, every new electron that I have, I'm going to have a new hole there, right? So they're going to be exactly equal to each other. However, now I see that the density of electrons is going to be much larger than the density of holes. So density of electrons is in the order of 10 to the power of 15 to 17. That means that the density of holes is going to be somewhere between 10 to the power of 3 to 10 to the power of 5, right? And that kind of raises the question that why the number of holes is actually reduced so much. Yeah, I understand why the number of electrons is actually increased because, well, I've added all these phosphorus atoms in it. They're going to have a lot of free electrons. They're going to introduce a lot of free electrons into my crystal. But why the number of holes are actually gone down so sharply? Well, the answer is actually quite easy to find. Well, the holes are actually filled up by these extra electrons, right? So if you had 10 billion electrons and 10 billion holes initially, and then you added, I don't know, 100,000 billion more electrons into this crystal, well, that 10 billion holes are going to be filled up very quickly, right? So at the end, you're going to have a lot less number of holes. And that's not going to even affect the number of free electrons at all, because, you know, again, if the number of free electrons is, let's say, 10 to the power of 15, well, if I subtract it from all the holes that I had in the beginning, still it's around 10 to the power of 15, right? Because this is, for those of you who don't see the math, just by looking at this, if I factor out 10 to the power of 10, this is going to be 10 to the power of 5 minus 1. So this is 100,000 minus 1, 99,999. So I can still say this is pretty much 10 to the power of 5. So this is almost 10 to the power of 50. Okay. Because of this, for these type of extrinsic semiconductors, I'm going to call one type of charge carrier the majority carrier and one type the minority carrier. So the majority carrier here is, so for N-type semiconductors, electrons are majority carriers and holes are minority carriers. So unlike the pure silicon crystal, which, well, they were equal, here we see that, well, one of them is much more than the other one. And the last question is that can holes become majority carriers? Well, you can think about it, and the answer is quite intuitive. So you can think about it, and yes, of course. So if instead of introducing a phosphorus atom of group 5 into my crystal, silicon crystal, if I introduce a group 3 material, then instead of having an extra electron, I'm going to have a shortage of one electron, meaning that an extra hole in my covalent bonds, right? So that's what we're going to talk about in the next slide. So here's the p-type kind of extrinsic silicon or p-type semiconductors. Here, instead of introducing a phosphorus or group 5 kind of a material, I'm introducing a boron atom into my silicon crystal. Therefore, I'm going to have an extra hole here, right? So that's going to be the majority carrier for these type of crystals, right? So we're going to call these crystals p-type or positive type kind of crystals or extrinsic silicons. The acceptors, so we're going to call these atoms, instead of donor, we're going to call them acceptor. Acceptor atoms, and the density of these acceptor atoms, I'm going to call it Na. The density of boron atoms. Okay, and you can imagine that the density of holes in these crystals is going to be equal to, more or less equal to, Na, and the density of electrons is going to be Ni squared divided by Na. Okay, or well, Na being P, right? So the density of holes, P, is equal to Na. Therefore, the number of electrons is going to be Ni squared over Na. Okay, so nothing new here. It's just the opposite of what we discussed before. Now, one question, or you can think of it as like a micro quiz kind of a thing, is that think about what happens to an N to the N and P of, or meaning the density of electrons and density of holes in an N-type material when temperature increases. So we know that for an N-type material, before temperature increase, I have N, the density of electron, equal to number of donors, and P, the density of holes, is equal to Ni squared divided by Nd, right? What will happen if I increase the temperature, right? So what would be the new N and what would be the new P? Of course, I don't want you to actually calculate an actual number, but what do you think is going to happen, like in terms of like increasing, decreasing, remaining constant, and things like that? Try to think about it for, well, let's say 30 seconds or 1 minute, and then, well, resume the video and we'll talk about it together. I hope all of you have tried this and have thought about it. So if you think about it, when I increase the temperature, think about what happens when I increase the temperature. When I increase the temperature, I'm going to have more of these electrons that are stuck to the covalent bonds break away, right? So I'm going to have more and more electrons, more and more free electrons there that are actually the result of basically breakdown of a covalent bond, right? Not because of the impurities that I've added, right? So it means that when T goes up, I know that my Ni increases, right? So the number of free electrons that are there because of the temperature increases, right? In like the number of free electrons that could have been there even if this was a pure silicon crystal, right? But then if the number of electrons are increasing and Ni is, well, in the order of 10 to the power of 10, and it's increasing, let's say, even by a factor of 10, right? It becomes 10 to the power of 11. Does that change the number of the density of my free electrons? When the density initially was Nd, which is somewhere around 10 to the power of 15 to 10 to the power of 17? No, right? So if I want to plot this, and this is the temperature, and initially, and this is basically the density. If the density of electrons initially was here, if I increase the temperature, this more or less remains constant, right? How about density of holes? Well, if you think about it, the number of holes initially was, well, somewhere around here, right? Now, if I increase the Ni, it actually increases the number of holes significantly. Why? Because Nd remains constant. So if Ni is actually increased by a factor of 10, Ni squared increases by a factor of 100. So the number of holes is actually increasing very quickly. So you can think about it, if the number of holes or the density of holes were down here, very close to 0, you can think about it with temperature, I'm going to have more and more and more holes. Okay, so this is N and this is P. So it takes, of course, this is an exaggerated plot. It takes a lot of temperature increase to get the number of holes even close to the number of electrons. But the idea is that for an N-type material, or for an extrinsic material, an extrinsic semiconductor material, if I increase the temperature, the number of majority carriers pretty much remains constant, but then the number of minority carriers actually increase with temperature. That's the lesson that we wanted to learn. So if this was a p-type material, if I increase the temperatures, the number of electrons would have been increased. The number of holes were, well, more or less pretty much constant. Okay.